MCMC is in many ways a very powerful and almost magical algorithm, but it's also as unreliable as my first car. There are a bunch of ways that it can go horribly wrong. Let's start with the simplest of them. Our starting value is invalid. Here, we start the Markov chain to be larger than b, our right truncation point. Asking for 1000 samples spits out some warning. If we look at the first part of the chain, it's just staying at the same point. The histogram shows that this continues on for all 1000 samples. We never move off the starting point. If we do one individual jump and print out the values, we can see that the acceptance probability alpha is 0 divided by 0, and Python will always say that any uniform random variable is not less than this not a number threshold. It's quite easy to start the Markov chain inside the support of our target distribution. However, it's still easy to choose a very bad starting point for the chain. To demonstrate, let's look at the same Weibull distribution but only left truncated, and start the chain at a large value of 1000. We update the pi variables and run the sampler. The histogram doesn't agree with the target PDF very well in this case. The target PDF would seem to indicate it being very unlikely to see samples larger than 100, though our X sample has a large fraction of samples bigger than this. If we plot the samples as a time series, then we see the problem. The chain starts at 1000, which is a highly unlikely place given the target density we have, and it eventually moves towards more likely double-digit values. But this takes some time. After about sample number 60,000, it seems that the chain has settled down, or in the terminology of Markov chains, it looks like it has reached its stationary distribution. This kind of plot is called a trace plot. One way to fix this bias towards large numbers is to throw away all the samples before the chain reaches stationarity. This is called the Burnin period, or I've also heard it called the warm-up period. Plotting the remaining samples, we see something that looks like a sequence of independent random variables. They aren't independent, but we'd prefer our samples to be as close to independent as possible. Comparing the histogram of the later samples against the target, we see a much better agreement of the two. It's impossible to look at a trace plot and be able to perfectly determine if a Markov chain has reached stationarity. Markov chains are strange. They can spend a very long time in some region, which makes us think that it's reached stationarity, but if we run the chain for longer, we see that it in fact has just taken a long pit stop on the road towards its actual stationary distribution. This is some phenomenon called quasistationarity, My Australian PhD advisor Phil Pollitt is a world expert in this field. One practical way to alleviate this problem is to start multiple Markov chains from different starting positions and check that they all eventually converge to the same region of stationarity. Here we start 4 chains and store the results in the matrix X. Plotting the trace plots together, we see that the blue, yellow, and green chains all converge to the same region, so they likely reached stationarity after about sample number 4000. Whereas the red chain, which started at the value of 310, is wastefully wandering around a region of low probability. This indicates that 310 was a bad starting value for this particular problem. Running again with smaller starting values shows that the 4 chains become indistinguishable after about sample number 2000. And so we waste less computer time by choosing the smaller Burnin value. Taking the remaining samples of each chain and putting them together using reshape, we get a final sample size of 32,000.